Hello everyone. We are now going to begin our lecture on the fourth section of chapter 2 on set theory. Now in the previous section we had talked about Venn diagrams, but those Venn diagrams were for two sets. This time we are going to work on Venn diagrams with three sets, and we're also going to follow that up with a few other topics, one of them being the verification of equality of sets, and we will also learn about De Morgan's law, which is used on set complements. All right, so let's go into this section and start learning about Venn diagrams with three sets. So here are the three topics we said we would learn in this section. One was to construct a Venn diagram with three sets, and then we will learn to use Venn diagrams to verify equality of sets, and finally we'll talk about the De Morgan's laws for sets. Now, before we go into talking about Venn diagrams for three sets, I just want to review what we learned about Venn diagrams in two sets. If you recall, for Venn diagrams in two sets, we had our rectangular box here. And this rectangular box represented the universal set, which contained all the elements related to a particular study, a particular topic. All right. So we had the universal set represented in a rectangular box, and within that we had represented two sets as circles, correct? There was one set, we call that A, and then there was another set intersecting the first set, and we call that B. All right, and within the circles there were three regions, and I'm going to kind of make the circles a little bit bigger. So just give me a few seconds here, all right, to fill in this rectangular box. Let's make this circle bigger, and we call the first set, or the first circle, A, which represented set A, and then there was another circle which represented set B, and they partially overlapped, the two circles, and we saw that within the circles there were three regions, correct? And we named them region 1, region 2, the intersecting section was region 2 and region 3, and anything not contained within the circles was region 4, correct? So we learned about three regions when we worked with, we learned about four regions essentially, three regions inside the circles and one region outside, but within the rectangular box. So we essentially divided uh, the diagram into four regions. When we are working with three sets, however, you see over here we have three circles, circle A, then set B with this pink circle here, and then we have set C represented by the black circle. So look at the regions we have. So they all overlap each other, not completely but partially. So there's region 1, region 2, region 3 like we had before, but then there are four other regions, 4, 5, 6, 7, and anything not contained within the circles is this outside region, all right, but within the four walls of this rectangle, that's region 8. So when we work with Venn diagrams with three sets, we end up with having 8 regions. So when three sets overlap, 8 regions are created.
Now that we know how the Venn diagram for 3 sets looks like, and that the Venn diagram for 3 sets create 8 regions in all, we are going to go over each region one at a time to determine what elements should be put where. All right, so we'll first consider the region which is labeled 5 here. All right, as you can see that this region where the 3 arcs intersect and kind of face each other, all right, you see the arcs encompass this region. They are all concave over here, the arcs. In this region, we are going to include all values which are all elements that are common to all 3 sets. So set A, set B, and set C, all the elements common to the 3 sets will be included in region 5. So to determine the elements to be placed in region 5, we include all common elements to the 3 sets, and we denote that as A intersection B intersection C. Again, if you recall, another word to represent intersection is A and B and C. All right, and is another term used to denote intersections. So it's in the region 5 where we will be including elements, all elements that are common to all 3 sets.
Next, we look at region 2. All right. So over here in region 2, it's the pink and the blue arcs that are concave. All right. So that means set A, the arc for set A and arc for set B are the ones that are concave. So this section, this region 2, is going to include all elements that are common to set A and set B. All right, so let's write that. 2 is going to contain, and let me use a different color here. 2 is going to contain elements common to set A and set B. All right, so what does it say here? It says determine the elements to be placed in region 2. So we have to find the elements that are common to A and B, which means A intersection B. That goes in region 2. We will now look at region 4, which is essentially bound by this black arc from the black circle representing set C and the blue arc representing set A, correct? So the elements that we are going to include in region 4 would be the elements that are common to set A and set C. So the intersection of set A and set C will be placed, the elements from those 2 sets will be placed in region 4, but only the ones that are common between the 2 sets. All right, so as you can see over here, there's the pink circle also bounding, but it's on the outside of the circle, correct? This region 4 is really on the outside of the pink circle. It's inside of the black arc and the blue arc. So that's how we know that it will contain the elements from set A and set C. Let's look at region 6 now. Region 6 is in the inside of the black circle and the pink circle and outside of the blue circle. So that tells us that it's going to include all elements that are common to set B and set C. So it's going to be B intersection C. And we are going to find all the elements. If we were given an a set or given three sets, the elements of three sets, and we were asked to find what elements we should put in region 6, then we would look for the common elements between B and C and place them in region 6. Now let's look at region 1 and 3 together. All right. So in region 1, we are going to include all elements that are unique to set A only. So there's no commonality. The elements that are not common with any of the other sets but are unique to set A goes in region 1. Likewise, in region 3, we are going to place all elements that are unique to set B. That means there are no elements in set B that are common to set A or set C are going to be placed. Those elements are going to be placed in region 3. And for region 7, we are going to place elements that are unique to set C. And finally, in region 8, the elements outside of set A, B, and C, but a part of the universe, right? Region 8 represents the set of universe, the universal set of values that we are working with. So any value which is not a part of set A, not a part of set B, and not a part of set C would be placed in region 8. So here again they are talking about region 3 essentially, and they are saying that we should include elements from set B which are not a part of region 2, region 5, or region 6. All right. So 2, 5, and 6 exactly. So anything outside of these regions are going to be placed in set B, which means the elements that are unique to set B and they don't have any commonality between set elements in set A or elements of set C should be placed in region 3. Again, region 7, which is the bigger portion of the circle C, will contain elements unique to C. That means elements that are not common to set A and set B. So it'll be values or elements that are not in the regions 4, 5, or 6. And finally, elements in region 8 are all those elements in the universal set that are not included in set A, set B, or set C. Now the book illustrates the three set Venn diagrams using an example from biology, and it's on blood types. So human blood is classified according to the presence or absence of the specific antigens A, B, and Rh in the red blood cells. So there are three types of antigens in our blood: A, B, and Rh, and they will represent three different sets. All right. Now will be some interaction between the three sets to form different or more variations of the blood types. Anyway, the antigens, the three broad antigens in our blood are A, B, and Rh. Antigens are highly specified proteins and carbohydrates that will trigger the production of antibodies in the blood to fight infection. Blood containing the Rh antigen is labeled positive plus, while blood lacking the Rh antigen is labeled negative. All right, so we will look into a Venn diagram or look into constructing a Venn diagram that will encompass all the different blood types from the three sets A, B, and Rh. So let's go through all the possible blood types from the three sets that we discussed, or using the three sets that we discussed. So in set A, all right, set A is only blood type A. Set B will have the B, and and then there's the set for RH, correct? That will only have positive or negative, all right? And all combinations of A and B will have either a plus or a minus, or okay? Now, given that, we can have an A plus, all right? We can have a blood type which is A plus or A minus. We can have a blood type which is B plus or B minus. Okay, and blood types which are not A or B, which does not have or which do not have the antigens A or B, they are known as O plus, all right, O plus or O minus. Now, we can have combinations of A and B, and for that we can have AB plus or AB minus. That's an additional one. So if we have three sets here, all right, let's say we have these three sets. And let's draw another one for. So let's put the RH here, which is set C. All right, set C. And the red one is for type B and the blue one for type A. Then all the A minus will be in this section, in this region, all right? All the minuses will be over here. So this is going to be B minus, all right? And we are going to have O plus here. And this region, region 2, is going to be AB, all right? It's going to be AB plus. This is going to be AB minus. And then there is going to be A plus, and there's going to be B plus, all right? And anything outside this is going to have O minus, all right? And that's a part of the universal set. So what I'm going to do here to go over this Venn diagram is first list the universal set of blood groups, all right? And then we will pick the elements from the universal set to make sure that they have been placed in the right regions. So first I'm going to pull up the information here, and then I'm going to write out the universal set denoted by U, and that's going to be the set containing A plus, A minus, B plus, B minus, then there's going to be an AB plus, an AB minus, and then O plus and O minus. So this is a complete set of elements that fall under the universal group. So let's see what they have done here. So blood containing the RH is denoted with the positive sign. Blood without the RH is negative. This will be denoted as negative. So A minus, B minus, these without the RH would take the negative sign. All blood in the RH circle is positive. All right, so this is the RH circle. So we have three circles or three sets, set A, set B, and set C, or set for the RH. So this one is the set for RH, and it will only contain the positive All right, and then set B will be the set of B's, and the set A will contain all the A type of blood groups. Okay, so let's look at what elements they have placed in which region. So region 1 has A minus, all right, A minus. Then region 2 has AB minus, right? It's the intersection between just A and B. So it'll take the A, it'll take the B, and it is outside of the plus region R8 circle, right? It's outside of the R8 circle. So it'll be AB minus. And then region 3 has B minus, okay? Because it's the unique B, it does not intersect with A or with RH positive. Let's look at region 4, which intersects with A and with positive RH, right? So that would make it A plus. So region 4 will contain the blood group A plus. Now, region 5 intersects with all three circles. So it has A, it has B, as well as RH positive. So region 5 is the common intersection between set A, B, and C. Mind you that set C has only positive RH. It contains RH, therefore it's considered to be positive. Then set region 6 is an intersection between set B and set C, correct? The RH set. So it'll be B plus, all right? B from here and the plus from here. Anything which does not intersect with A or B in set C will be just positive. So it will be called O positive. And outside in region 8, we have O minus. So that does not belong to any set, any of these sets, A, B, or C. So we put that in region 8, which is a part of the universal set. Okay? We will now go through an example to determine whether two sets are equal to each other or not using Venn diagrams. So the two sets given to us here are A intersection B naught, also termed as the complement of A intersection B, whether that's equal to A naught, that is the complement of A, union B naught, or the complement of B, for all sets A and B. So we will first start by sketching the Venn diagram and also determining or identifying the four regions that go with Venn diagrams of two sets. All right, so I'm going to draw my rectangle here. All right, so here's my rectangle, which represents the universal set, and then we'll have two sets, the blue circle for set A and a red circle for set B. And let me just label the circles as A and B, A and B. And now let's label the four regions, right? So this is region 1 on the extreme left hand side. We have region 1, then the intersection of the two regions, the overlapping area between A and B is region 2, and then there's region 3, which represents elements that are unique to set B, and there's no overlap with elements in set A. And finally, anything that falls outside the two sets is in region 4, right? So anything outside the set A and set B would fall under region 4. Okay, so now that we have our sketch here with the regions labeled correctly, we will go ahead and uh, identify the regions or associate the regions with the sets or different forms of the set. So we'll start with A first, all right? So set A, all right? Set A covers which regions? All right, so elements that belong to set A would be region 1 and region 2. So even though that's an overlapping area, but still the elements of set A are in this region. So 1 comma 2. So let's write that. It's 1 comma 2. What about B? All right, so which regions correspond with set B? That's 2 comma 3, correct? So we'll write that as 2 comma 3. That's 2 comma 3. And then we will determine what A intersection B is, or what region that corresponds with. Just A intersection B, all right? We are not looking at the complements as of yet. So A intersection B would be just this region, which is region 2. All right, so let's write that, region 2. All right, now we are going to look at the complements of these three regions. So region A complement or A naught would be which ones? Anything outside of 1 and 2 would represent A naught, correct? So what are the regions which are not 1 or 2? It's region 3 and 4, correct? So A naught would be represented by region 3, comma 4. Likewise, B naught would be the regions outside of 2 and 3, the regions other than region 2 and 3. B is 2 and 3, so B naught will be all regions which are not 2 or not 3. So that would be 1 and 4. So I'm going to write that here. 1, comma 4 would represent B naught. And then we have to also determine A intersection B naught. So A intersection B naught was region, or rather A intersection B was region 2. Therefore A intersection B naught, or the complement of A intersection B, would be everything other than region 2. So let's list those regions: 1, 3, and 4. Okay, so now we are trying to determine whether this statement is true or not. So A intersection B naught, right? So let's write that. That's what we are trying to determine. A intersection B naught, whether that's equal to A intersection B, sorry, A complement union B complement, correct? A naught union B naught. So I'm going to list the regions that we found to be, or which fall, which correspond to A intersection B naught over here. So I'm going to just write 1, and let me use a different color perhaps, 1, 3, and 4, correct? Let's list the regions that correspond to A naught. That's 3 comma 4. So let's write 3 comma 4. And then union B naught or B complement would be 1, comma 4. Correct? So we write that out. Remember, when we do a union, we do not repeat the same values. If there are two values, then we just write one of them. So 1, 3, and 4 is how we are going to write that. So it would represent region 1, 3, and 4. Correct? So what do we have here? A intersection B naught was 1, 3, 4. A naught union B naught, or A complement union B complement, was also 1, 3, 4. Therefore, the two sets are equal. So we just proved using a Venn diagram that these two sets are equal. Now here is the solution that the book provides to us. So let's see whether they have provided or they have worked it out the same way as we have or not. So first here we can see that they drew the Venn diagram for set A, set B. They've marked the 4 regions. So now we are going to see how they go about proving the equality of the two sets. Let's look at the next step of the solution. We have a picture inset over here of the Venn diagram. Again, the regions all labeled. So first, they're trying to find A intersection B complement. So the complement of A intersection B, kind of the way we worked, all right? So again, for set A, the corresponding regions are 1 and 2. So that means all elements that belong to set A can be found either in region 1 or region 2, and they have the two regions here. The elements that belong to set B can be found in region 2 and region 3 also, region 2 or region 3. So 2 comma 3, they've uh, they've labeled the corresponding regions here. They've written out the corresponding regions here. And then A intersection B is this overlapping region, and that's region 2, so they have that written out here. And then A intersection B complement, so A intersection B, or the complement of A intersection B, are the regions 1, 3, and 4, right? Everything except this region 2, which represents A intersection B. All right, the complement of A intersection B would be all regions which are outside, which are other than region 2. So now they are trying to figure out A complement and then union B complement. So A complement would be all regions that are other than regions that correspond to A, right? So if there's 1, 2, 1, if A, the regions corresponding to A are 1 and 2, then the regions not corresponding to A would be 3 and 4, correct? So they have that 3 and 4. B complement would be 1 and 4, correct? 1 and 4. And A union, sorry, A naught or A complement union B complement would be 1, 3, and 4, correct? So here we have here 1, 3, and 4. Because 4 is repeating, you don't need to write it twice. So we see over here A intersection B naught is 1, 3, 4. A on this side, on the right hand side, A complement union B complement is also 1, 3, 4. So they've stated the final proof in the next slide. So let's quickly go over that. So here's how they've stated the final solution. It says both statements are represented by the same regions 1, 3, 4 of the Venn diagram. Thus, the complement of A intersection B is equal to the complement of A union the complement of B for all sets A and B. Now, the proof that we just came up with gives rise to a very important law pertaining to set theory. It's called the De Morgan's law. And the De Morgan law states that a pair of related theorems known as De Morgan's laws make it possible to change statements and formulas into more convenient forms. And what are the forms? It's the first one is A intersection B naught, or the complement of A intersection B, is equal to the complement of A union the complement of B. So this is the one that we just proved. The other one, there's a second one which says A union B naught, or the complement of A union B, is equal to the uh, complement of A intersection the complement of B. All right, so these two are special laws. They are termed as De Morgan's laws, and they are used a lot in set theories. All right.